Hello class, welcome to our lecture on derivatives of inverse functions. Now as we move into this lecture, first let's talk about the inverse functions. A quick recap is that inverse functions are two functions that are mirror images of each other about the y equals x line. So the y equals x line is actually a diagonal line right in the grid. So this is your y equals x line. And if I had a graph on this side, like this, its mirror image would be like this. So they are mirror images across the y equals x line. Okay. So what that means then graphically is that, and even algebraically, is that your x and the y coordinates get interchanged. Okay, interchange x and y. So what that means then again is, let's say we choose this point, okay? If this is, say, 0, 1, okay? I know it doesn't look like that, but let's say it was 0, 1. That will get flipped around, and this would be actually 1, 0. So that will be the mirror image in terms of coordinates. So your x and your y get switched around, and that's what makes them inverses, okay? And then there is also an algebraic property. Oh, by the way, the notation for inverse is f with a power -1. It is not f power -1. It's confusing, I know, but this notation is to be read as f inverse. It is not the same as 1 over f. Okay, it is not equal to that. So I've made that very clear there. It's sad that they had to use that notation because it's confusing, but it's to be read as f inverse. So if a function f and its inverse, okay, f inverse, okay, so f of f inverse of x, if you took their composition, if they are inverses, then the order of composition does not matter, and it will always result in that variable x that was the input for this function, okay? And that is a very important rule. Let me erase this part. So what we're saying is, if let's say this green upper graph is f, this one will be f inverse. It's called f inverse because it is an inverse of, or an inverse function of f. So we use the f and the f inverse notation. Sometimes we can call it g as well, right? For instance, you don't want to use this confusing f notation, you can call it g, where you have to make it very clear that f and g are inverse functions of each other. Then you can say this is true. Okay, I want us to also recall that inverse functions are the only functions that would produce an exact input variable x. Okay, 1 over x, 2x, x squared, all those mean that they were not inverse functions to begin with. Okay, so only for inverse functions is this interchangeability going to work. Okay, meaning when you take composition of functions, the order always matters. When it doesn't matter and it produces an x, we know they were inverse functions. And then lastly, we use a horizontal line test for testing if a given function has an inverse or not. The vertical line test tells us if the given graph is a function or not. A horizontal line test will tell us if the given function has an inverse or not. So you're going to perform the horizontal line, same as the vertical line test. It should not cross more than once on the graph. So that was our quick recap of what inverse functions mean. Now we come to derivatives. Okay, so we are talking about taking derivatives of inverse functions. Well, we're going to mostly look at it also in terms of trigonometric functions, because for other algebraic functions, yes, we can figure it out. But for trigonometric functions, we need to delve a little deeper. Okay, so we have something called the inverse function theorem. There is a derivation for this, but we're just going to look at we can look at the derivation for this because this basically comes from this property. But let me first write the theorem, okay? So the theorem kind of says, let f of x be a function that is both invertible and differentiable. If you look at that language, you know that invertible means that this function f of x has an inverse. Okay, we usually call that inverse f inverse, right? Or we could call it g, however we define it to be. And it should be differentiable, meaning you should be able to find a derivative for that function and its inverse. So we're saying let y be equal to f inverse of x. Okay, and let this be the inverse for f of x. Okay, this is where we define what we're going to call the inverse to be. So I said let y be equal to f inverse of x. If you did not want to use the inverse notation, you could then call it as g. So you can say let g of x be the inverse for f of x. That will set the record right. Okay. And then we add an extra condition because it's a theorem. We can see that this won't work under certain circumstances. This is a trivial circumstance, but what we're saying is this is true for all x, such that these are all shorthand notations. Don't worry about it. You can pause and replay the video to know what those stood for. F prime of f inverse of x is not equal to 0. Okay, so we want it to be differentiable, the function, but we don't want it to be differentiable at f inverse of x. Okay, meaning we don't want it to be, we want it to be differentiable, we don't want it to be equal to 0. Okay, so we don't want a horizontal tangent at that. All right, so this is the theorem actually, dy over dx. We're calling y as f inverse of x, so we are replacing the y with f inverse of x. So another notation for that will be f inverse prime of x. Right? Just showing you all the different ways in which we can write this. And here's the theorem. The theorem says that's going to be 1 over f prime of f inverse of x. Okay. If you were using the g notation, it's slightly better looking, just because if g of x is used instead of f inverse of x, then you just say g prime of x, right? So the notation immediately looks a lot better. F prime of g of x. Okay. So how we derive this is going to come from the composition of functions property. This is basically a property of composition of functions where the only time that the order of composition would not matter and will always produce an x is when those two functions were inverses of each other. So we start from that to take the derivative and find this theorem. Now, just for the fun of it, let's derive this. Okay, so I'll just say derivation. So we know that x is f of f inverse of x, right? I mean, where did I get this from? Right from here, from this property, right? See here, f of f inverse of x is the same as f inverse of f of x equals x. So I've taken the first part equal to x. So that's our premise. We're starting from there. And this is a property, so we don't have to substantiate this anymore because this already is a property. Okay, so we're going to take derivative on both sides. with respect to x. So just want to show a little elaborately. So I'm going to use colors here. So I'm saying you're taking the derivative on both sides. Right? So the derivative of x would come out back as 1. But here you have f of f inverse of x. So you can see that they're kind of nested, and this triggers chain rule. And so if you're using chain rule, the chain rule allows you to take the derivative of the outside times the derivative of the inside, right? So let's again use colors. So this clearly is the inside, and this would be the outside, okay? And then let's write it by the side here. Chain rule basically in words would mean derivative of outside times derivative of inside. So because of that, now we need to take the derivative of the outside, which is f prime, right? Outside is the f, so take its derivative and keep the rest as it is. So that's the derivative of the outside times the derivative of the inside. So the inside is f inverse. So f inverse, you need to take its derivative to complete the chain rule, okay? And that's basically it. So we now need to find, or rather isolate the purple, okay? So I divide both sides by f prime of f inverse of x. That leaves us with, I'll bring this to the left. F inverse prime of x is 1 over f prime of f inverse of x. And this is the inverse function theorem. If you take this and compare it to this formula that we just wrote here as part of the theorem, they match up. So the derivation for this is fairly simple, very easy. It's just taking the property of inverse functions and finding derivative on both sides. Now let's say we are asked to find the derivative of g of x, which is x plus 2 over x. Okay, we need to find its derivative. So we need to find g prime of x. Now what we are told is we can find this derivative either directly by differentiating using the quotient rule, or we could use the inverse function theorem to find the derivative. Okay. So what does that mean? Well, for algebraic expressions like this, right, it's a rational function. So for these kind of ones, honestly, using the quotient rule would be a quicker way out, okay, rather than using the inverse function theorem. But I just want to illustrate that here to indicate to you that this may not be a very useful technique for these kind of expressions, but inverse function theorem comes in handy when we deal with trigonometric functions. Okay, so let me just show you what that is. Now g of x, okay, you have x plus 2 over x. Now if you need to find its inverse, what you need to do is, let's just call this y. I'm just showing the side calculation for this. And we know the rule was that the x and the y got interchanged. So this y will now be x, and all these x's would now become the y. Okay, so then you multiply by y on both sides, and then collect all the y terms on one side, isolate the y equals 2 over x minus 1. So you have solved for the new y. This is the inverse of g of x. Because it's the new y, we're going to call this g inverse of x. Okay, g inverse of x. Again, if the inverse notation bothers you, you can call it f of x if that's easier, because it's easy to switch between f and g rather than g and g inverse. because you also have the prime notation. We don't want this -1 and the prime notation to get mixed up, right? So it's your choice. But ultimately, what we do is we use algebra to actually find the inverse function, right? And then if you come back here, the inverse function theorem tells us that in order to find g prime of x, I will have to do 1 over f prime of g of x. Okay. I'm using f prime because I prefer to use the f notation than the g inverse notation. Okay, so that means I now have to find 1 over f prime of g of x. Now, what was g of x? X plus 2 over x. Okay, so in order to evaluate this, I have to first find f prime of x. Okay, so I need to find f prime of x and then replace this x with this x plus 2 over x. So I've got 2 steps to do before I could actually plug it into the theorem. So to get this, let me write f of x first. F of x is now 2 over x minus 1, which is the inverse function. Now, you can write this as 2 times x minus 1 power negative 1. I'm moving it up just so I can use the power rule and chain rule within it. Right? So you could do that, or you could do the quotient rule, but I think this is going to be quicker. So take its derivative. The derivative would be 2 times negative 1 times x minus 1. Negative 1 minus 1 is negative 2, right? I usually do the chain rule, but here you take the derivative of the inside. So I did the derivative of the outside. The power was the outside. Derivative of the outside times derivative of the inside, which comes out to be 1. So it was kind of redundant. So that's basically negative 2 over x minus 1 squared, right? Because the negative 2 is brought down to the denominator because we don't want the result to have a negative power. Get to this because that's what will give me the answer for g prime of x. I need to find it at x plus 2. Okay. So that's going to be negative 2 over, in the place of x, I now have to replace it with x plus 2 over 2. Okay. You have to do computation here that involves complex fractions, and then you do all the squaring. Let's do that quickly. X plus 2 minus 2 over 2 squared. That came out a lot easier. That leaves us with x squared over 4, which implies negative 2 over x squared times 1 over I apologize. I just realized that I had made a grave mistake. It was x plus 2 over x, not over 2, as I had mistakenly written here. Sorry about that. That's going to be x, not a 2. So I'm going to erase these things so we can write it correctly now. And it makes a world of difference, isn't it? So that's x plus 2 minus x over x. Okay. Notice how now the x's are the ones getting cancelled. Okay. So that's negative 2 over 4 over x squared, isn't it? So that's going to make it negative 2 over 4 times 1 over times x squared over 1. You take the reciprocal of the x squared, okay? And that leaves us with negative x squared over 2, isn't it? This would be a 2. And what was all this? This was our f inverse of x plus 2 over x, okay? But we know by inverse function theorem, g prime of x was basically this 1 over f prime of x plus 2 over x. So then I have to write this as 1 over, and this answer actually goes to the denominator, negative x squared over 2, which would be basically negative 2 over x squared. That is the answer for g prime of x using inverse function theorem. Okay, this is roundabout only because it's asking us to first find the inverse of g algebraically and then find its derivative and then take its reciprocal. Okay. So we don't appreciate this as much only because there is an easier alternate to this. The alternate would be that, okay, maybe it's going too far off for us. Let's just maybe do it here. So I'll just say or, and I can say quotient rule, right? Quotient rule. So let me write, what was the original function? G, right? G of x. So let me write g of x as x plus 2 over x. This was our g of x. Excuse me. We were asked to find g prime of x, which means I'll have to use the quotient rule, where this will be my u and this will be my v. U over v derivative would be u prime v minus v prime u all over v squared. So u prime is 1 times x, times x, which is our v, minus v prime, that also is 1 times u, x plus 2, all over v squared, which is x squared. So I'm going to bring that in here, and that's going to be x, distribute the minus x minus 2 over x squared. X and minus x will cancel off, negative 2 over x squared. We got that same answer in a jiffy, right? So as I mentioned, the inverse function theorem is more suitable for trigonometric functions than for other algebraic expressions. Okay, so then let's go to the actual use of this inverse function theorem. So then let's maybe take a look at a trigonometric example. Let's say we are asked to find the derivative of, let's call it g of x again, of sine inverse of x. Okay. So what's going on here? So now once again, if you talked about the inverse functions, right, and just the sine inverse, we've seen this notation in trigonometry where sine inverse of x, sometimes it's also known as arcsine of x. Just maybe to avoid that -1 notation, right? That's confusing. Maybe that could be the reason why they started using arcsine, or it could be the reason that the typewriters couldn't do that kind of notation insert, so they could have done this. It's just my imagination, the need for a different notation. Well, what we learned was sine inverse of x in trigonometry is the inverse of the sine function. Okay. And when you did the inverse, remember sine functions and cosine functions are wave patterns, right? They just go as waves. So if you did the wave, the vertical line test passes, right? That's good. But if you did the horizontal line test, notice how it hits at more than one place, right? So the horizontal line test fails. So we said, well, we can take this wave pattern, but then we will have to restrict it in such a manner that the vertical line test and the horizontal line test will work, right? So that's a quick recap. Therefore, what we figured was, well, if you took the inverse of sine, where x fell in this interval negative pi over 2 to pi over 2, right? That's just one period, but you can look at that, such slices, so that it's over this particular interval for choices of x that you can find the inverse, which is a function as well. So, it passes the horizontal line test. So what we're saying is we can find inverse for trigonometric functions, but they must happen over a particular domain. Okay. So now we're asked to find the inverse of sine here using the inverse function theorem. So then let's use a new notation. Let's say f of x. Let f of x be equal to sine x is the inverse of g of x equals sine inverse of x. Okay, so I am defining my f of x to be the inverse of the sine inverse. With me on this? I know it's getting a little confusing with all the extra inverses, but we're using a special notation, f of x, and calling it sine x, because sine x is the inverse of sine inverse of x. Okay, all right. Now with this, we need to find, according to inverse function theorem, I need to find g prime of x, which is 1 over f prime of g of x. Okay, this is the theorem. So I'm trying to work towards this. And as you can see clearly, we need to find the derivative of f and evaluate it at g of x in order to get this g prime of x. And it has to happen in the denominator and all that. Okay, so let's come here. Now, let's again do it by the side. Now, f of x is sine x. So f prime of x will be cosine x, right? The derivative of sine is cosine. Okay. Now what we're going to do is we need to find f prime of not x now, but the x must be replaced by g of x. Now g of x is sine inverse of x. Oh, wow. So that is going to be cosine of sine inverse of x. We need to find that information. Okay, how do we do that? Well, we have to then, just before we get to that, I just wanted to also bring this to the same format, f prime of sine inverse of x. Okay, and that'll be 1 over cosine of sine inverse of x. I'm matching it up so that when we get the answer, we can just insert it here into the step. All right, so coming to the right-hand side, I need to find the cosine of the sine inverse of x. So we always start from the innermost, okay? So we're going to explore what this would mean. Because it's trigonometry, we will draw a right triangle. And remember, sine inverse of x is some angle, right? Let's call that angle theta, okay? So sine inverse, so let's just say let theta be sine inverse of x. That means sine theta is x. Agreed? I'm trying to use this theta notation so that I can use the right triangle. All right. So because it's a right triangle, I'm trying to use the idea of opposite over hypotenuse, which is the definition of sine, in order to affix the sides. So opposite over hypotenuse, I want to drop a 1 underneath this so that x corresponds to the opposite, which is x, and the hypotenuse is here, which is 1. Agreed? So sine theta is opposite over hypotenuse, x over 1. Now, once we get this information, This is sufficient for us to find the third side, which is the square of the hypotenuse minus the side square. That's a Pythagorean theorem, isn't it? Which is the same as square root of 1 minus x squared. So just to clean up that triangle a little bit. So this is x, 1, and square root of 1 minus x squared. All right? So from this, what is cosine of theta? Cosine of theta is adjacent over hypotenuse, which is square root of 1 minus x squared over 1, which is basically square root of 1 minus x squared. Okay, wow, this gets dragged down deeper. All right, so we have cosine theta, which is cosine of, what did we define theta to be? We defined it to be sine inverse of x. So we defined it to be sine inverse of x. And we just found theta, cosine theta to be square root of 1 minus x squared. Okay, and that's it. So you have the information you need to bring it back into the step. The step is 1 over this cosine expression. So it's 1 over 1 minus x squared. So on the left, we had g prime of x to be 1 over square root of 1 minus x squared. So to put it all together, if g of x is sine inverse of x, then g prime of x came out to be 1 over 1 minus x squared. Now, isn't that fantastic that you started with something that looked complex, but you got a relatively simpler expression? Well, it's got the square root, it's got the fraction. That's relatively simpler compared to a trigonometric function. So your result did not contain any trigonometric functions. And I think that is definitely a simpler version, isn't it? And this was possible because of the inverse function theorem. Right? So as we saw, it has its place here as opposed to algebraic functions, because those could be achieved easily using quotient rule. You could find the derivative. But here, to find the derivative, you still had to go a bit roundabout, because you had to then utilize concepts from trigonometry and then insert it into the inverse function theorem. However, the good news is that this derivation really helps us to come up with a similar argument for other trigonometric inverse functions or inverse trigonometric functions. So I'm just going to list them all here for you. So I want to put this crisply. So d over dx of, or meaning derivative of sine inverse of x, is the same as 1 over square root of 1 minus x squared, right? That's really nice and crisp. And you can write similarly for cosine inverse of x. And what's beautiful is you can use the same concept, the same triangle, right? The one thing before you could use this triangle is this derivative part. So if I started with cosine x, right, then the derivative of cosine will be a negative sine x. And so that is where you get the negative in the answer for this one. So negative 1 over square root of 1 minus x squared. This is the formula, but you can see where the negative comes from. So that's going to be a negative sine x if you started with cosine x, right? So negative sine x. And if you come all the way down, negative sine x, right? You could use the same argument, right? Same argument. So this will all be flipped now. This is going to be a sine of cosine inverse of x, right? And if you follow along those lines, it will produce these answers. So if you, using the derivation actually helps us to generate all these other inverse trigonometric functions. 1 over 1 plus x squared, and so on. Okay, we have the formula sheet that's in the course, so you can actually use that to figure out how we got the others. D over dx cosecant inverse x. So in future, you can actually use these shortcuts to get your answer. Some of them will look a little complicated, but we are not deriving them per se. But if you wanted to derive them, not a big deal. It will involve a lot of algebra in addition to to trigonometry. Secant inverse of x, 1 over absolute value of x, x squared minus 1. And then lastly, cotangent. So cotangent inverse x. Now, where does the, notice how the x squared minus 1 has changed. It was 1 minus x squared this side, but that side is x squared minus 1. We also have the absolute value of x. Notice that these are all already reciprocals of the functions on the left, isn't it? So if it's reciprocal, then you already have a flip. And then to that, you have the inverse added. So there are double layered restrictions that fall on it, and therefore the players have changed accordingly to produce these derivations. Okay. So moving forward, you can, cautiously start using these formulas whenever you need to find the derivative of inverse trigonometric functions. So let's do a couple of problems just to help us utilize these formulas that we painstakingly found. Okay, so the question says, find the derivative of h of x equals x squared times sine inverse of x. Okay, so it looks complicated because you now have x squared being multiplied to the sine inverse. But then because of the help we just had, we can actually handle this more gracefully. So you're trying to find h prime of x, for which you'll have to use the product rule. So your u is your x squared and your v is your sine inverse of x. So uv prime is u prime v plus v prime u, your product rule. So I'm just going to insert the answer here, so that's just less repetition. Okay, u prime is 2x, u prime v, sine inverse of x, plus v prime. So sine inverse of x, you're trying to find its derivative. So I come over here. The derivative of sine inverse of x is 1 over 1 minus square root of 1 minus x squared. So 1 over square root of 1 minus x squared. That's v prime times u, right? V prime u. U is x squared. So just clean that up. 2x sine inverse of x plus x squared over square root of 1 minus x squared. And that is the answer. That is it. We did the hard work, the heavy lifting before, and therefore now we can just enjoy the fruit of our labor by just utilizing the formula into our product rule. Let's take a look at another example where, let's say, the argument for the inverse function was a little different. So let's say, for instance, s of t is given to us to be tan inverse of 1 over t. Okay, it's not a plain x, but you have something else. In fact, I'm using s here to kind of indicate that it is the position function. So they're asking us to find the velocity. If they ask us to find the velocity, s prime of t is velocity, v of t, right? That is velocity. So if they simply say find the velocity, they're basically asking us to find the derivative of s. So s prime of t is taking the derivative of old habit, dx. Its derivative with respect to t. Okay, tan inverse of 1 over t. Now for this, we'll have to remember the chain rule, right? The chain rule substitution. So we've got to do derivative of the outside times derivative of the inside. So the derivative of tan inverse, right? Let's go back quickly to see what the formula was. The derivative of tan inverse is 1 over 1 plus x squared. But here we have not x, but 1 over t. So 1 over 1 plus whatever this is, right? That squared. That's the derivative of the outside times derivative of the inside. Inside is 1 over t, So you need to take its derivative. So I'm just going to write that in one more step, 1 over t. Okay, and let me just mark that out here as derivative of outside times derivative of inside. And that's always your chain rule. It's always triggered when you no longer have a simple variable x or a simple variable t. Instead, it's appearing differently with added information like 1 over t or t squared or whatever. Right? All right, so now that we have that, now this is 1 over t, so you can move this as t power negative 1 and do the derivative. So I'm just going to skip to the step. So 1 over 1 plus 1 over t squared times negative 1 over t squared. That's the derivative of 1 over t. So if you clean this up a bit, I get t squared over 1 plus t squared plus 1. Right? I took the LCD here, drop a 1 underneath it, take the LCD here, and then you get a t squared in the bottom, which will get flipped up to the top. And so that leaves us with t squared on the top, t squared on the bottom getting cancelled off. That gives us the velocity as v of t, which is basically your s prime of t, as negative 1 over t squared plus 1. Sometimes they can, add something more to the question and say, find the velocity at t equals 1 second. Okay, so I'll just add that here. Find the velocity at t equals 1 second. So if they add more context to it, it basically means you want to evaluate t at 1. So negative 1 over 1 squared plus 1, which is basically negative half. So we can drill down further into the question by adding these extra evaluation pieces. But notice how the procedure is still the same. Okay, where does the calculus part come in? The calculus part comes in when you are taking the derivative, right? It tells us the chain rule. So we apply the chain rule upon using the formula for tan inverse. So we're using two things. This is the formula for tan rule, and this is the further extension of it for the chain rule. So derivative of the outside times derivative of the inside. And then when you simplify it, you're now switching to algebra, where you try to handle, complex fractions, and then simplify them and reduce them to their lowest terms. And then if there is more question to it, then make sure that you evaluate at the given value and reduce your answer to produce the final result. If they ask you for units and all that, that could be another added thing, because velocity is distance over time, isn't it? Yeah. So they didn't give us the information on the distance here, so that's why they didn't ask us for the units. But let's say the distance was measured, like for instance, the position here, right? Let's say it was measured in, let's say, meters. So that's going to be meters per second, negative half meters per second, or something like that. So that will be the additional extra things that you might be asked in a word context, word problem context. I hope that was helpful. Thank you, class.